In the vast and mysterious universe, events occur so powerful that they defy our understanding. Today, we are going to dive into the phenomenon of supernova. To understand the enormity of supernova, we first need to visualize what actually happens. Imagine a star immense, with overwhelming gravity and unimaginable internal pressure. Inside the star, there is a constant struggle. On one side, gravity trying to compress everything towards the center. On the other, the energy of nuclear fusion, generated in the core, pushing outwards. A supernova occurs when this balance is broken. In the case of massive stars, when their core runs out of fuel, it collapses under its own gravity, resulting in a colossal explosion. This explosion releases an unimaginable amount of energy, causing, for a brief moment, the star to shine brighter than its entire galaxy. To begin to understand the causes of a supernova, it is necessary to delve into the bowels of a star. In the core of a massive star, constant nuclear fusion takes place, turning hydrogen into helium and producing energy in the process. As the star consumes its hydrogen, it begins to fuse heavier elements, from helium to carbon, from carbon to oxygen, and so on, until iron begins to form. Iron is a tipping point. It cannot be smelted to release energy. The core becomes extremely dense and unstable. Without the fusion energy to counteract gravity, the core suddenly collapses, and this violent implosion then triggers a massive explosion, the Type I supernova. On the other hand, we have white dwarfs. When two of them, in a binary system, come close enough together, they can merge, or one can accumulate matter from the other. When the combined mass of white dwarfs exceeds a critical threshold, another fascinating form of supernova results, known as a Type I supernova. In the universe, beauty is in diversity, and that extends to the world of supernova. In a simplified way, we can divide supernova into two main types, Type I and Type II. But the story is more complex and fascinating. Astronomers classify supernova based on their light spectra. If we don't see lines of hydrogen absorption, we're looking at a Type I supernova. If we see it, it's a Type II. Type II, on the other hand, occurs in massive stars that have exhausted their nuclear fuel and have their cores collapse. There are even more subcategories, such as Type I and Type X supernova. They are similar to Type II in that they originate from massive stars, but differ in the absence of hydrogen or helium in their spectra. Although scientifically categorized and studied, each supernova is a unique event, a luminous signature of a star's death, contributing to the eternal cycle of creation and destruction in the cosmos. When we look at a galaxy, we see countless stars. But imagine for a moment that a single point in this galaxy outshines all the other stars combined. That point of intense, sweeping light is a supernova. At its peak, it can emit an amount of light comparable to that of billions of suns. For context, the brightness of a supernova can outshine that of an ordinary star by more than 100,000 times. It can be so luminous that, for a brief period, it outshines the entire galaxy where it resides. But that spectacular glow has its duration. It starts with an intense peak, and over weeks to months, gradually decreases as the energy of the explosion dissipates. Throughout history, various cultures have witnessed the emergence of new stars in the night sky, which were in reality supernova occurring in our galaxy, visible even during the day. Each supernova is a reminder that even in death, stars have the power to light up the cosmos with a final, spectacular farewell. These are the remnants of supernova. They are composed of gas, dust, and high-energy particles, all interacting in a cosmic ballet. When a star explodes, it hurls its outer layers into space at incredible speeds. Over time, this matter interacts with the interstellar medium, forming complex and often beautiful structures. An iconic example is the Crab Nebula, remnants of the supernova observed on Earth in the year 1544. Even after nearly a millennium, its splendor continues to fascinate astronomers and enthusiasts alike. But supernova remnants are not just beautiful cosmic landscapes. They are natural laboratories. The extreme conditions inside them accelerate particles to speeds approaching the speed of light, helping us understand high-energy phenomena in the universe. Each remnant, with its unique shape and color patterns, tells the story of the star it was, the power of its explosion, and the legacy it leaves behind in the fabric of the cosmos. When we talk about supernova, we often focus on their spectacular destruction. However, it is from this destruction that the fundamental building blocks of life and new stars are sown. During the life and death of a star, chemical elements are formed. A supernova explosion then disperses these elements into the vast void of space. Oxygen, carbon, nitrogen, iron, many of the essential elements for life on Earth, have their origins in the furnaces of stars and in supernova explosions. In addition to being sources of chemical elements, supernovae play a crucial role in the formation of new stars. The shock wave from a supernova can trigger the collapse of nearby molecular clouds, starting the formation of new stars and potentially planetary systems. In a very real sense, we and everything around us are made of star stuff. Supernovae played a role in shaping the elements that make up our planet and even our bodies. The next time you look up at the night sky, remember, we are all products of the stars. Supernovae in their death sow the ingredients of life, connecting us to a vast and wondrous cosmic legacy. In our quest to understand the vastness of the universe, we have found supernovae to be valuable tools. They are not just spectacular phenomena. They are also cosmic lighthouses that help us to probe the confines of space. A special category of supernova, type Ia, have an intriguing characteristic. They explode with an almost uniform brightness, becoming standard candles in the cosmos. Why is this useful? Well, if we know how bright they are intrinsically, and we look at how bright they appear to us, we can deduce how far away they are. It was precisely using type Ia as supernovae that astronomers made a surprising discovery in the late 90s. The universe is not only expanding, but this expansion is accelerating. This revelation, based on observations of distant supernova, was so monumental that it resulted in the Nobel Prize in Physics in 2011. He highlighted the role of supernovae as fundamental tools in modern cosmology. Supernovae, in their cataclysmic explosion, are not just the end of a star, they are often the prelude to the formation of some of the most intriguing objects in the universe. Depending on the star's original mass and the amount of matter left after the explosion, the remaining core can take very different paths. If the remaining core has a mass even about twice the mass of the Sun, it could collapse into a neutron star. These are incredibly dense, with the mass of the Sun compressed into a radius of only about 10 kilometers. However, if the remaining core is even more massive, the collapse continues until all matter is swallowed up by an infinitely small and dense point, a black hole. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. They can continue to grow, feeding on surrounding matter and even other stars. So, while the death of a star in a supernova might seem like a tragic ending, it's really just one step on the cosmic journey, leading to the formation of even more mysterious and fascinating celestial bodies. Supernovae are reminders that, amidst the vastness of the cosmos, the birth and death of stars are cyclical events and fundamental to the tapestry of the universe. Thanks for joining us on this stellar journey. If you liked it, like, share, and subscribe for more space explorations.